morning all. My name is Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR IT, Hyderabad, India. So today our topic is LC filter, combination of inductor and capacitor filter. So let us see the overview of today's session. So we start with the filter concept again, then inductor capacitor filter combination, and then conclude with summary. So let us start with the filter concept. We know, so why we need filter? In order to remove the ripples from the rectified output of any rectifier circuit, we require filter circuit. So in order to minimize the ripples in the rectified output of any rectifier circuit, we require a filter circuit. Why we need to remove these filters? Ripples. So ripples are time varying with time. They are varying with time, so they are not desirable. So we require DC signal. So in order to get this pure DC signal, we require a filter. So actually the output of any rectifier circuit is not exactly pure DC. It's a pulsating DC. So this is a pulsating DC. If you consider here, this is pulsating DC. So this is a rectified output of a full wave rectifier. So if you apply this to a filter, so filters are many kinds: inductor filter, capacitor filter, and combination of those inductor and capacitor. So this is the actual filtered output. So in this you will find DC, pure DC. So let us start with the inductor capacitor filter, combination of inductor and capacitor. So it is also called as L section filter. So if you consider L section filter, previously we have discussed the inductor filter, single inductor filter. There the ripple factor is directly proportional to the load resistor RL. Whereas if you consider C filter, that is capacitor filter, ripple factor is inversely related to the load resistor. In contrast to these two, in LC filter, the ripple factor is independent of load resistor. So this is very important point. The ripple factor of LC section filter is independent of load resistor. So this is the circuit diagram for LC filter. L inductor is connected across the rectified output, and across the load resistor we have capacitor. So LC capacitor. Okay. So here, for a particular value of inductor, that either diode D1 or D2 will be conducted continuously at a critical value of the inductance. So this is important point. Either D1 or D2 will be conducted continuously at a critical value of inductance. So critical value means LC. Okay. So let us analyze this inductor capacitor filter. So from the Fourier series, the output voltage can be expressed. So the output voltage V0 can be expressed as V0 is equals to 2 Vm upon pi minus 4 Vm upon 3 pi cos 2 omega t. So here in this case, in this output expression, this will be the DC value, VDC. So here we have written VDC, that is DC component or average DC voltage is 2 Vm by pi. The remaining are AC component. So because since I already told you this, the rectified output is a pulsating DC, so which consists both DC and AC. So this is VDC and this is AC component. So the DC output voltage, let us consider in this IRMS. So if you consider this AC component 3 Vm by 3 pi, so this the amplitude is 4 Vm upon 3 pi. So this is your peak voltage of the AC component. So from this we can calculate IRMS. So what is IRMS? IRMS is IRMS is equals to VRMS into RL, because VRMS by RL, because we know V is equal to IR, so I is equal to V by R. So here IRMS is equal to VRMS into RL, and we know what is VRMS. VRMS is Vm by root 2. So this VRMS is equals to Vm by root 2. So from this data we can write IRMS is equal to 4 Vm 3 pi by root 2 into 1 by XL. So this is the reactance across the load as a inductor. So inductor reactance is here the impedance 1 by XL. So from this here what is Vm? So we know that VDC is equals to Vm by pi. Okay. So 2 Vm by pi in case of full wave rectifier. So therefore from this Vm can be written as VDC into pi by 2. So if you substitute here, so what happens? 4 Vm by 3 pi root 2 can be written as root 2 by 3 into VDC by XL after substituting all these values. So therefore this root mean square current flowing through the capacitor, that is this one. So this current flowing through the capacitor XC, so creates a ripple voltage in the output. So therefore VRRMS, that is AC component, this is called AC component or root mean square value of the AC component present in the output. So VRRMS is equals to IRRMS into XC. So we are talking about at this point. So XC is the reactance of the capacitor. So and then we can write a root 2 by 3 VDC into XC by XL. And therefore from this we can write ripple factor is equal to VRRMS by VDC. So already here VDC is there. So VDC gets cancelled. So finally you will get this value. Root 2 by 3 XC by XL. But we know what is XC. XC is equals to 1 by 2 omega C and XL is equals to 2 omega L. So therefore we can write a root 2 by 3 1 by 4 omega square CL. So this is the ripple factor of the LC filter. So for example, if you further analyze, let us consider frequency is 50 Hz. So we know omega is equal to 2 pi f. Okay. So f is equals to omega by 2 pi. So therefore we have f value, f 50 Hz, and C if you measure in microfarad and L in henries, then the ripple factor can be simplified as rho is equals to 1.194 by LC. So if you know the value of L, inductor value and capacitor value, then you can find the ripple factor. That means it shows the how many number of ripples present in the rectified filtered output. So next we can analyze further this circuit LC filter with bleeder resistor. So for a critical value of inductor, either diodes, that is diode D1 or D2 is always conducting, that is current does not goes to zero, falls to zero. So the incoming current consists of two components. One is DC value IDC is equal to VDC by RL, and the second one is a sinusoidal varying component with peak value of 4 Vm by 3 pi XL, just we have discussed. So the negative peak of the AC current must always be less than DC component. So that is root 2 IRMS, that is AC component must be less than or equal to VDC by RL, that is IDC, DC component. So AC component less than or equal to DC value. So therefore, so this is the circuit diagram here. So this is the bleeder resistor. Actually, for example, this condition not satisfied all the cases. So let us see what happens. See here, we know that for a LC filter, IRMS is equals to 2 root 2 by 3 VDC by XL. Hence, 2 VDC by 3 XL less than or equal to VDC by RL. That is XL greater than or equal to 2 by 3 RL. That means what? LC, that is LC, critical inductance value, critical inductor is RL by 3 omega. So for example, if there is no load, so that means resistance is infinity. So when at no load, that load resistance is infinity, the value of the inductance will also tend to be infinity. So this is the critical case. That means it should not be happen. So this is not desirable. So to overcome this problem, a bleeder resistor RB is connected in parallel with the load resistor like this, in parallel with the load resistor. So what happens now? It improves. A minimum current will always be present for optimum operation of the inductor. So there is a current flow through even the resistance is infinity because of this bleeder resistor. And one more important point is it also improves voltage regulation of the supply by acting as a preload on the supply. So this is one of the advantages of bleeder resistor. And it also provides safety by acting as a discharging part for the capacitor. So unwanted AC component will not be available at the output because of this reason. So because it provides safety acting as a discharging path for capacitor. Otherwise, you will get AC ripple component in the output. So filtering cannot be done if you are not providing this bleeder resistors. Okay. So this is about bleeder resistor, advantage of bleeder resistors. Now let us see another important. So we can also improve the filtering nature of this rectified output with the multiple LC sections. So better filtering can be achieved using 2 or more L section filters. So here we know that now if you see this here, L section, C section, L section, C section. So two combination, multiple LC section filters are used. So these L section, why just like a L section filter. Okay. So because of this, the ripple factor also improved. So the expression for if you apply the same analysis which we have done for the single L section filter, then finally you will get ripple factor as root 2 by 3 XC2 by XL1 XC1 by XL1. So if you know the values of this capacitor values L1 L2 C1 C2, then obviously you will get the ripple factor. Similarly, for a single LC, we know that for single LC filter the ripple factor is given. So this is for contrast. So for comparison of the multiple LC filter with the single LC filter, so we have written like this. So VRRMS by VDC root 2 by 3 XC by XL. So the combination will improve the filtering further. Okay. Next comes to CLC or pi section filter. So we can also increase the filtering of the rectified output using different combinations. So here it consists, the CLC consists a capacitor filter followed by an LC section. So if you observe the circuit diagram of this CLC or pi section filter, so it looks like a pi section filter. Okay. So it consists of a capacitor filter followed by a LC filter. Simple. One capacitor and LC section. So combination of capacitor LC section. So therefore it is called capacitor CLC or pi section filter. So the construction look like a pi. So we can say pi section filter. offers a fairly smooth output is characterized by a highly peaked diode currents and poor regulations. So of course it gives more filtering of the rectified output, but it gives the poor regulation. So that is the drawback with this combination. So proceeding further the analysis in the same way as that of single L section filter, we can also get the ripple factor expression as this one. Rho is equal to root 2 XC1 by RL1 RL and XC2 by XL. So here please remember, here we are using RL load resistor, not XL. Okay. So the term RL in the above equation should be noted, because so in the previous case we have used XL. So here only one combination, that is capacitor and load resistor, and then capacitor and inductor, CLC. So again, if you consider frequency of the wave is 50 Hertz and capacitor is measured in microfarad and inductor in henries, then RL in ohms, then we can directly calculate the ripple factor as 5700 by L C1 C2 RL. So it is easy to understand that. So directly calculate the ripple factor using this expression. Okay. So therefore, so let us conclude this. So we have started with filter concept and then combination of filters. Combination means we have a inductor capacitor filter and multiple. So inductor capacitor filter is also called as L section filter, and multiple L section filters we have discussed, and then we have analyzed LC filter, and then we have calculated the expression and we have derived an expression for ripple factor, and then we have discussed the inclusion of bleeder circuit. So what is the advantage of bleeder circuit, bleeder resistor, and then CLC and pi section filter we have discussed, and CLC pi section filter gives more smooth the filtered output but poor regulation. Okay, so all these topics we have covered in this today's session, and next topic will be clipper circuits. Thank you.